In the classical mechanics and the quantum mechanics of spherically symmetric potentials, we're used to the SO3 symmetry giving rise to angular momentum conservation. But when the spherically symmetric potential we're dealing with is specifically the 1 over r potential corresponding to an inverse square force, something strange happens. There's an additional weird conserved quantity called the Laplace-Runge-Lenz Vector, which indicates additional symmetry beyond just the usual SO3. For convenience, let's specialize to quantum mechanics so that we can use the observables not just as operators, but specifically as generators of the symmetry groups that lead to their conservation. If we work out the algebra of not just the angular momentum operators, but also include the components of the Laplace-Runge-Lenz vector operator, then we find, if we recast it in the right way, that the symmetry group is actually SO3 direct SO3, which is isomorphic to SO4 over Z2, rather than just a single factor of SO3. So the symmetry group is actually quite a bit larger than the spherical symmetry, the obvious symmetry of the problem, and the symmetry that applies to all spherically symmetric problems would make clear. Now, because it's the continuous part of a symmetry group that actually gives rise to conservation laws, you'll often hear people just say O3 instead of SO3, or O4 instead of SO4, or SO4 over Z2. And it's also important to note that the discussion I just gave applies to bound states. O4 gets replaced by O31 for scattering states. But of course, the bound states are the most commonly studied case, both in classical mechanics and quantum mechanics. In a future video, I might show you that interesting mathematical story in some detail. But in this video, I'm going to do what I often do on this channel and focus on something that I don't see covered elsewhere. And that is the derivation of a number of important relations satisfied by the Laplace-Runge-Lenz vector operator in quantum mechanics that usually are just stated without proof. Now, it's true that they skip the derivation of these relations in, for example, textbook treatments of this topic for a reason. Most of the physical content isn't actually seen in deriving them, and actually doing the derivation is fairly long-winded and complicated. However, it's always good and satisfying to be able to prove something yourself, and if you're a student, you may well be asked to do this, much like I was, as a homework assignment. So, I'm going to show you how to do it. Okay, so I decided to do the Hamiltonian commutator calculation first because it turning out to be 0 is really the most important of the relations I'm going to derive for you. It's the one that you insert into the Heisenberg equation of motion to show that the Laplace-Runge-Lenz vector is quantum mechanically conserved. This is the famous Laplace-Runge-Lenz vector, and because it's only conserved in the 1 over r potential case, the one we're studying, that gets us this Hamiltonian. Now, in this calculation, we have to break apart the big commutator that we want to calculate into a bunch of smaller commutators, and then insert what we know for the values of those, and then simplify. And that process is way easier if we use index notation. And we'll also use this identity for Levi-Civita symbols a lot. Given this breakdown of the cross product in terms of index notation and a Levi-Civita symbol, we have this result here for the Laplace-Runge-Lenz vector. Oh, and there's actually one other thing that I forgot to mention. The reason why we've got two terms here is actually to ensure that the quantum mechanical vector operator is Hermitian. If we were to go to classical mechanics, then of course L and P would commute. We would be able to reverse the cross product at the cost of that minus sign. They would add, and we'd get rid of the factor of 2, and we'd have the quantity that we're familiar with from classical mechanics. The next thing I did was I actually opened up the momentum operators as well with more Levi-Civita symbols. Then I factored out the 1 over 2m there, and I reversed indices on this Levi-Civita symbol here to get it ready for use of this identity, and that got rid of the minus sign. If we insert it, we get here, and then simplifying down using index juggling, which you're probably familiar with if you're watching a video like this, gets you immediately to here. So now we're ready with our simplified index notation expression for the Laplace-Runge-Lenz vector, inserting that directly into the desired commutator along with the Hamiltonian, also written out in index notation there, we can start breaking down this commutator. The first commutator rule that I applied is one that allows you to break apart sums. It gets us from here to here, and we see that we already get one of the constituent commutators canceling just because all of these are C numbers and they definitely commute with themselves. I then did some trivial simplification to get this, and then I noticed when I was doing this calculation that these were going to be fairly long to expand, and that doing it in the whole expression probably wasn't the best idea. When you're doing long, intricate calculations, success can often really depend on keeping your algebra organized so that you don't make needless mistakes that are really hard to track down. So what I did was I came up with these C quantities here. I think just because that's what the word commutator starts with, but regardless I numbered them so that then I can keep track of exactly which term I'm referring to. Then I started a table, and I just simplified each one of these down by expanding them out, first with this product rule for commutators, and then inserting the commutator values that I knew, and then doing whatever index juggling was required, and of course it simplified down to this much smaller thing. If we were to do this in the original expression and most of the commutators worked out to be something this long, it would be much more nasty to do. I again did that for C2 and it worked out very similarly, C3 and C4. Now to do C5 and the others, it's actually a bit non-trivial because we have commutators of this form when we actually expand it out. But there's a fun identity for commutators of position functions with the momentum operator. It turns out that this commutator is actually just equal to minus I, the gradient of whatever function is in this part of the commutator. So we can just evaluate that. I'm not going to prove that formula here. I'm already showing you enough complicated algebra, but it actually isn't that hard to show. So now let's actually employ it. I used the product rule to expand this out again, and then I just inserted the results I calculated up here. They didn't simplify down as much as C1 through C4, but I mean sometimes you don't get lucky. This is what C6 turned out to be. Then we have C7, C8, and C9. Then now all we have to do is simply insert it all back in and see what we get. So this is what we get. The first thing to notice is that all of these terms actually cancel each other out, so this whole 1 over 2m squared term vanishes entirely, and we're just left with this. Now, not everything cancels in this case, but it does get a lot better. I've color-coded the terms that cancel each other so that then you can see what I was doing very easily, and it reduces the entire thing we started with just down to this. So while this isn't 0 yet, it is at least a lot better than what we were looking at before. The next thing I noticed when I was doing this calculation is that when you use the position momentum commutator to reorder this PL and that RI, you get a cancellation, a very convenient cancellation between the reordered term and this term over here, which, well, is just this one, and the expression we started with. This reduces these two complicated, nasty terms to this much simpler term. The next key steps that I made were perhaps not very obvious. I commuted this P to the other side of that, then I commuted this P to the other side of that. That, of course, gives you these commutator terms that compensate for the fact that R's and P's don't commute in quantum mechanics. The reason why this is non-obvious isn't because those steps are hard to carry out. It's non-obvious because it's hard to tell that that's going to help you make more progress. But it turns out when you insert these in and do any index juggling you need to do, it's pretty quick to see that all the remaining terms cancel and you get that this commutator is in fact equal to 0, which is very satisfying. Now on to the next relations in that list I showed you at the beginning. The process is essentially the same. We start by writing out the quantity that we want to evaluate in terms of index notation, and then we just work with what we see. We try to figure out ways of getting closer to what we already know the answer is likely to be, being careful to keep our algebra well organized so that we don't make a bunch of mistakes that are hard to track down. Writing everything in index notation is pretty easy, and in this case, for the most part, I actually don't explicitly write out the L's in terms of Levi-Civita symbols. and r's and p's. I only do that in this term here because it makes it very quickly obvious that this term is equal to 0. Ri and rj multiplied together forms a symmetric tensor because they're both the same and they commute with themselves, and that's contracted with the Levi-Civita symbol, which of course just vanishes because it's antisymmetric. In order to handle these terms, though, I had to do something a bit trickier. The first thing I noticed is that if I moved this I all the way over to the end, and of course that's two minus signs so they cancel, then I end up with pj times the cross product of L with itself, which actually isn't 0 because they don't commute. The other thing I noticed I could do is I could, at the expense of a commutator, move this p over there and get another cross product, which I've shown down here. The benefit of doing this is now we know how to proceed. We need to evaluate this, and then we need to evaluate these L cross products and see what that gets us. First of all, the L cross products are actually really easy to evaluate because directly from this famous commutation relation, we get its value as just I-L vector. And actually, I remembered right about now that I did a bunch of these calculations in natural units, so if you're wondering where all the H bars are, they're all set equal to 1. There's only one calculation later on where I didn't use natural units, just because the answer looked so much prettier with the h-bars in it. Now you may ask for that calculation why I didn't just insert h-bars in at the end if it's just the pretty result that I was going for, and the answer is I probably should have done that, but didn't for reasons that I can no longer remember and probably weren't that good anyway. Now getting back to the calculation we're currently working on, this commutator is relatively straightforward to evaluate, but we do have to open up this L operator here and then use the product rule for commutators again in order to actually be able to evaluate it. The first term vanishes, so we don't get a two-term result. That's always nice. And this one is just the usual value. Do remember the minus sign there because the p comes first. And then with index juggling, we get this answer, and we're ready to insert everything back in. We can see that those cross products of L's simplify down very nicely to much easier to deal with dot products. And this term also gets quite a bit easier to deal with given that the Levi-Civita symbols are double contracted with each other, so we've just got a very, very simple substitution in there. All it does is give us another L dot P term, and if we combine like terms we end up with this, which is looking a lot like a commutator. If we write it in index notation, it's even more obvious that it's a commutator, at least if you assign the dummy indices correctly. We can then write it as a commutator, substitute the value we already calculated for this exact commutator, and then notice that we have a Kronecker delta, which is symmetric, double contracted with a Levi-Civita symbol, which is antisymmetric, and that vanishes the last term that remains, and we wind up with the result we're going for. Now you may think, well, dot products are symmetric. Can't you just reverse it to prove that the other way is actually also 0? And the answer is, well, this is quantum mechanics. These operators don't commute, so it's not so simple. Let's actually calculate out what the reverse is. We'll find that it does happen to be equal to 0, but we couldn't just assume that. Now, I've done essentially the same process all over again. It's so similar, there's no reason to try to come up with something new. You can pause the video if you want to look through it. The important thing is that we do in fact get 0 again. Now on to number 3. This is actually the one where I left the h bars in just because I think it looks prettier. And I'm not going to delete them now, so I guess we'll just have to deal with it. Now the process here is similar to before in that we eventually do break it down into index notation to do a lot of the calculating. However, I didn't actually do that immediately. I found that waiting a little bit led to better organized algebra and therefore a higher probability of not making a dumb mistake in a complicated calculation. The first step, of course, is to insert the Laplace-Runge-Lenz vector in and then to multiply it out, being careful to respect order because of a lack of commutativity. We can then do only a little bit of simplification. This r dot r is just r squared, which cancels that r squared in the denominator, leaving us with just a constant term here at the end. And at this point it was pretty obvious that this expression is nasty enough. I was going to have to break it up again, much like I did in the first calculation. And so I labeled the pieces I was going to break it into and then created a table. Also, in an effort to keep my algebra organized, I saw it as useful to pre-calculate some of the identities that I was going to be using repeatedly in simplifying this monstrosity, so that then I could just apply them later rather than inserting these calculations somewhere in the middle of the algebra or even trying to write this out in the big expression. My reason for picking these particular identities to prove is that there's a lot of different terms in this expression that differ by the ordering of the L and the P. So I figured it would be quite useful if I knew exactly what term I had to add or subtract in order to validly reorder them given their non-commutativity. From there, I just inserted these results in and then simplified. After seeing this simplified expression, it was apparent to me that there were a few other quantities that I should pre-calculate separately before proceeding further. Specifically, these two triple products here. And here's where you get into the interesting results of non-commutativity. This one turns out to be non-zero, but then this one turns out to be zero. So you couldn't just assume that because of the usual symmetry of the dot product that you could move this p over to the other side and get the same result. It doesn't work out that way, as you see when you actually do the calculation. Inserting these values back into A gives us a much simpler result. This is looking, actually doable now, although we do have, as you can see below, some nastiness still left to deal with because this quantity isn't exactly very simple. My strategy with this one wasn't too clever. It was really just one of brute force. Express everything in terms of index notation and then see what I can come up with. Express everything in terms of index notation and then see what I can work out. So first I expressed the obvious cross products in terms of Levi-Civita symbols and then applied that same identity we keep reusing, and then I wrote the angular momentum operators in terms of Levi-Civita symbols, after which index juggling led me to this. I then distributed and started messing around with commutation relations in the first term here. If we move this PL here past this RR here, of course it commutes with the PS, then we get kind of an interesting simplification. The entire resulting term turns out just to be equal to P squared times L squared. Of course, this does come at the expense of this additional term. However, that one actually ends up zeroing out. Notice that this delta ij relabels this r index to j, at which point we have this contraction between a Levi-Civita symbol and two factors of the momentum operator which commute with each other, so this whole thing is just straight up zero. All we have to worry about then is this last term here, and again we can mess with commutators to resolve that one. The basic strategy with this one is also to move PL past R sub R here, and this time the commutator term we have to add to make that valid also ends up vanishing. So all we have is this term left to worry about. Unfortunately, this term still isn't in a form that's immediately obviously anything meaningful, so we're going to have to mess around with commutation relations again. It turns out the key one to make is to commute Pj past Pr. The reason why that helps us is because if we look at the Levi-Civita symbols in here, after we, of course, insert the commutator value in this term, we realize again that symmetric products of P contracted with Levi-Civita symbols cause both to vanish. I didn't actually even bother to explicitly commute this Ps past that R sub R, because by now we realize that the actual commuted term will vanish for that symmetric reason, and the commutator that we have to add in order to actually make that valid is just proportional to a Kronecker delta and is also symmetric, so it will also vanish. We can just see that and skip writing out that step. We're therefore just left with the p squared L squared term, this entire complicated nasty thing that took us a bunch of crazy algebra to actually calculate works out to be something very simple, and this entire a term then just reduces to this. It's really quite satisfying how simple that ends up being, and we can also see that we're getting close to the expression for m squared that we know we're looking for. All we have to do now is calculate b, that other quantity that we used to break up the original expression into to organize our algebra. And again, we'll need these relations in order to do it. Applying it immediately converts the original expression for b into this one, which is a little bit easier because we've got fewer different types of cross product terms to deal with. The obvious next step is to try to work out what these triple products equal. With this first one here, we see that index notation makes quick work of that. It's just equal to L squared. This second one is slightly longer. If we reorder this cross product using the identity above, we can ultimately find this. And then it turns out this actual quantity here is a bit easier to evaluate. I put it in a separate box because it's yet another subcalculation. If we work this out, then we find that it actually equals L squared. But remember, this is just part of that original second quantity that we needed to calculate. If we insert it back in, we realize that this second quantity has two terms. It's not quite as simple as the first one we calculated. But again, that's what happens in quantum mechanics as a result of the non-commutativity. We can then insert these back into b, and we get a much simpler, much less scary expression that does look like it's starting to include some of what we need it to. At this point, it's useful to remember this explicit expression for the L squared operator, because from it we can see that there are no radial derivatives. Therefore, we can actually move this 1 over r, which is on the wrong side of this L squared, to the other side, and ultimately just get a 2 over r L squared. Of course, handling this term is slightly less easy because p and 1 over r don't commute, but we already evaluated the required commutator, so we actually can make quick work of it. And it ultimately just leaves us with a term proportional to 1 over r because this r dot contracts with that one, and we end up getting a cancellation that just leaves us with 1r in the denominator. At this point, we're almost done. All we need to do is mess with the ordering of these terms to get it to simplify just a little bit more. That ultimately leaves us with the expected two terms, this one, which gives us an r dot p factor, which causes this whole term to be the opposite of this one, so they cancel. And then we have this commutator term. But notice that this Kronecker delta is double contracted with this one, so we'll get a factor of 3. But also notice that it has the opposite sign to this term here. So it'll end up giving us a factor of 2 and reversing that sign, ultimately leaving us with this result. Simplifying a little bit gets us this final result for b. We can now do the really satisfying step of inserting the elegant expressions we got for a and b back into that original expression for m squared that looks so nasty to get the final answer. And of course, yes, it's what we set out to find. Now on to number 4, this nasty looking commutator. This calculation isn't like horribly long, at least by the standards of what we've just been dealing with, but when I was trying to figure it out for the first time, I did find it to be especially tricky, so hopefully this will help you. The first step is more or less what you expect. I wrote it all in terms of index notation and started expanding. I didn't actually have to expand these L operators anywhere because we already calculated the PL commutator, so I was able to get through the whole calculation by just applying that. To get from here to here, I simply applied the sum rule for commutators. It gives me two rather long terms. Only one of the simple constituent commutators actually vanishes, so I guess that's something, but we still are going to have to break up all of these nasty ones correctly without any errors in order to get this to actually work out. And that's where it gets tricky. The first step I did was just to pull out all the Levi-Civita symbols and then break it into these two terms, which I intended to handle separately. And again, I pre-listed some identities that are going to be useful in this process. Now, one of the things that actually tripped me up when I was doing this is the reverse commutator. I kept leaving a minus sign in there, but with the indices still in the order they show up in the actual commutator. But that's not correct, because when you actually do the process exactly, you find that you do get one minus sign from the commutator being reversed, but from reversing these indices back, you get another minus sign because it's a Levi-Civita symbol. So you don't have this extra minus sign out front that you might superficially expect to be there. It took me an embarrassingly long time to trace my errors back to that one mistake. So just note that and don't make that same mistake. Naturally, I handled T1 first, and the process was pretty simple. I used the commutator product rule to write out all the terms, and then I simply wrote above that what each commutator equals, and then inserted that in and simplified any way I could. This is, I guess, a little better, but we've still got plenty of work left to do. The key thing to notice is that if we multiply the Levi-Civita symbols in, we get a lot of Levi-Civita symbols contracted with each other, which means we can use that Kronecker delta identity to at least make a next step. Now, the step after this, actually, I did the reverse of what we've been doing a lot, and that is to write cross products and these standard vector notation things in terms of index notation in order to make it easier to deal with. I actually went back partly to the vector notation because I didn't have to parse as many indices in order to tell when two terms were of the same type. Again, here I highlighted like terms with color-coded highlighting so you can more easily see which terms are of like type in this rather nasty complicated expression. Two of them fortunately just turn out to be zeros, so I guess that's something. It turns out actually though that there are more like terms here than is immediately obvious. So before I proceeded to just try and deal with this, I played around with some identities that I thought I could use to reveal even more like terms. I ended up calculating a total of 5 of them, which are needed to show that so much cancels and the remaining terms recombine to something very simple. If we apply all these, this highlighting ends up turning into this highlighting. We can see that there are no terms that actually don't have any like terms to either combine with or cancel with, and the vast majority of them just straight up cancel out. Only these blue highlighted 4 terms are actually left. All the rest straight up cancel out and leave us with this gorgeously simple result, which, if you look back at the result we're trying to derive, is actually one of the terms we need. So it's going well. One of the terms we need simply comes straight up from T1. Of course, however, we're not done yet. We've still got T2. Again, I laid out some commutation relations here at the beginning that I definitely knew I was going to need, given what I was seeing in T2. This is T2. Now, T2 turned out to be intricate enough to calculate that I decided to break it apart into even smaller pieces. Let's start with TA. The first useful trick that I noticed is to factor this Levi-Civita symbol in, relabel dummy indices on this term here, and then reverse them on the Levi-Civita symbol at the cost of a minus sign. What we see is that L and P now have the same indices as they do in this commutator, which actually makes things easier later. Next, we can, at the cost of a commutator within a commutator, reorder these so it's straight up equal to that, getting us here. That leaves us with double contracted Levi-Civita symbols, which simplifies things down pretty nicely. Next, it's useful to expand this commutator out using the commutator product rule. With that, we're left with only commutators that we definitely know how to evaluate. Inserting them, and I guess simplifying a little bit, leaves us with this. I actually opted out of doing very much simplification because I found that waiting till later was more useful. It's not obvious that that would be the case. You basically just have to mess around with it. I'm giving you the benefit of me having already done it before. Next, we can handle TB in a very similar way, and it gives a very similar answer. Then we can insert that back into T2. We get a nice cancellation immediately, but we are still left with a fairly nasty expression. After playing with it for a while, I found that it was useful to just straight up insert these Kronecker delta identities in for these contracted Levi-Civita symbols. That's not always the right move. It wasn't obvious that it was the right move to get this to simplify down. I stared at it for quite a while, but it turns out it got me to where I needed to go, so I went with it. Now, these two yellow highlighted terms don't completely cancel with each other, but the first parts actually do. We can just get rid of those and insert the second parts, and then simplify a little bit. That ultimately leaves us with this, if we also rewrite some of those Levi-Civita contractions as cross products. I did that basically just because I found it slightly easier to deal with. Here, it's not a huge difference, but I still found it convenient. After staring at this expression, I noticed that this term is the one that I want, and that these two were going to have to cancel. This clearly didn't cancel, so it was going to have to cancel against whatever this simplified down to. So the pressure was on to figure out a way to simplify this down to something that was the negative of that. The first step I tried, I didn't really know exactly what was going to work, but I just had to try something, was simply to expand this out in terms of r's and p's. I figured working with the most basic constituents might give me an idea on how to proceed. It doesn't work out to be anything especially pretty or simple, but it does look closer to the kind of term I'm looking for than what I started with, so I figured it was likely progress. Fortunately, upon inserting these two back into this quantity here, it was much clearer how to proceed. To start with, these two terms canceled, and the remaining one actually had that factor of r squared in front of it, which would reduce the powers of r in the denominator to the right number, and in the parentheses here we see exactly what we want to see. Inserting this back into T2 unfortunately does reveal one remaining problem. The 1 over r is on the wrong side, but we know how to deal with that with commutation relations, and we see quite fortunately that when these commutator values are multiplied by their respective values of r index, they end up being equal but opposite and just cancel. So we're almost done. We have the 1 over r's on the right side. But when we actually combine it all and we look at what we've got in here, they don't cancel. However, look closely. These two terms are commutators. And when we actually evaluate those commutators, they do cancel, and we get exactly just the remaining term that we want. T2 gives us the other term that we need. If we remember that this commutator was just T1 plus T2, and we insert that in, do a bit of factoring, recognize the Hamiltonian, we do in fact get that final answer we're looking for. And with this, we're almost done. We've just got one more relation in that list to prove, and fortunately, that one is actually much less horrible than this one was. Unsurprisingly, the first step was to insert the formulas written in index notation and then apply commutator rules. In this case, it was relatively simple because there's only a single term here and it only has a single factor in it. But we do have two factors on the other side in a lot of these, so we do still have to expand some things out. The one exception is this one, which we can just insert in immediately because we already evaluated it above. Applying the commutator product rule gets us the rest of the way through the actual commutator evaluations themselves. From there, all we need to do is simplify. It may look like the only thing I did between here and here is factor out an I, and actually you're almost correct. I did move this Levi-Civita symbol to the other side of the P. I don't have any idea why I actually bothered to write out that trivial step, but whatever. Next, I multiplied this Levi-Civita symbol in. I reordered a few indices, which changed signs, to make it easier to then substitute in these Kronecker delta formulas, which I then directly inserted and then did the required contractions, at which point it was apparent that 4 of the terms canceled. After that, I was left with just these 4 terms within at least this first overall term, and it was clear that they didn't cancel. But upon staring at it for a while, I noticed I could uncontract some Kronecker deltas, and when I factored it correctly, I would end up with Levi-Civita symbols, and those were necessary because I was actually looking for both cross products and a Levi-Civita symbol left over to factor out, which is exactly what I was left with. Notice how we find exactly the formula for the Laplace-Runge-Lenz vector which we were looking for. The only non-obvious part about this calculation, the part that kind of tripped me up, was realizing that I needed to use this Levi-Civita formula backwards, which I rarely ever have to do. And with that, we have proved the last of that list of Laplace-Runge-Lenz vector operator formulas that we set out to prove. Hopefully this video has helped you get through these calculations in a shorter amount of time than it took me. Thanks for watching.